Good afternoon, students. Welcome to our webinar session. I am Swamy, Faculty of Physics, borabanda-boys. So today we will start with the last chapter, that is kinetic theory of gases. This chapter deals with the motion of the gaseous particles. This gives the relation between microscopic particles and macroscopic properties. It gives the relation between microscopic properties and macroscopic properties like speed, momentum, energy, etc., and pressure, volume, temperature, etc. So these are the properties of the gaseous particles or molecules. So the study of this gives the concept of kinetic theory of gases that we are discussing now. So in this, just before beginning to this, we know the material or matter is of three states that we know, that is solid state, gaseous state, and liquid state. So in among these three cases, in the case of solid, the particles are very closely packed, so they cannot move, and the motion is restricted, and we can see the shape of the solid. And in the case of liquids also, those are loosely packed, the particles are loosely packed, so that's why the shape of the liquid is as the shape of the bowl or a container. And now coming to the gas, is the shapeless, so their motion completely random. So now in this chapter we are going to discuss how the properties are changing in this. Means completely we are discussing the motion of the particles. The title is kinetic theory of gases. I told you it gives the relation between the microscopic properties and the macroscopic properties. So here I have given some examples: speed, momentum, energy, and the pressure, volume, temperature, etc. So here is given that usually the gas consists of huge number of identical, very small, spherical, neutral, and elastic particles. I'm repeating, gas consists of a huge number of a similar kind of very small, spherical in nature, neutral in charge, and elastic properties called molecules. Right? So with this, the gas is full of molecules with these nature, that is identical, small, spherical, neutral, and elastic in nature. Now in a gas, the molecules moves in all possible directions with all possible speeds. That you know, that in the gas, all the particles will move with different speeds in different directions. There is no specific direction in this. So here comes the distance between any two gas molecules is. I am repeating, in the gas molecules that we discussed, the interaction of the molecules is strictly say that no interaction, means they will move with different directions. Okay, so the distance between the molecules or the particles is very huge, so there will be no interaction, and that's why you cannot see the shape of the gas. So here comes the measurement here. The distance between any two gas molecules is nearly 10 angstroms. So 1 angstrom is equal to 10 power minus 10 meters. So hence there is no force of attraction for gaseous molecules. So this is the reason why the interaction between the molecules fails, because the distance between them is nearly 10 angstroms. Right, so there is no perfect shape for the gas. This is the reason. Now, the gas molecules are free to move, and they possess with the thermal energy due to temperature. So, with this energy, the molecules are continuously under motion. So, who is giving energy to these particles to move in random direction is because of the temperature. So I'm repeating, these molecules are free to move and they possess with the thermal energy called temperature, and this is the reason why the molecules are continuously under motion. considering, now we are just going deep into the concept now. So now we are just, our discussion is constrained to a small area that now we are considering an ideal gas. Okay, so consists of n number of molecules. Okay, we are considering a container, right? So in which we are considering n number of molecules and each molecule having some mass m. And enclosed in a container is in the shape of a cube, that is cubical box with a certain volume. Okay, so the cubical box having certain volume, so it is kept with, means the box is filled with some gas. It consists of n number of molecules, and each molecule has a mass m. So due to their random motion, they do collision with each other. We know the gaseous molecules moves in random direction, and see, you can see the diagram here that a particular molecule or an atom moves in a different directions. So while it is moving from one point to another, it may collide with a number of neighboring particles along with the walls of the container. Right? So with this, what we can see that the gaseous molecules moves in a random direction. So while they are moving from one point to another, means just we are zooming apart. So in that direction, this molecule or a particle will make a number of collisions with the neighboring particles along with the wall of the container. Right? Now the distance between any two successive collisions is called free path. Distance between any two successive collisions is called free path. Right? And the average distance traveled by the molecule is called mean free path. So I told you that, for example, the molecule is moving from one point to another. So while reaching from one point to another, it may make number of collisions, and to reach the another position, it is covering a distance, making number of collisions. So that average distance is called mean free path. So these molecules move with a certain velocities and each having mass, so that momentum comes into the picture. That, see, I told you that the molecules move with a certain velocities and each molecule has some mass. Then you can say the product of these two is a momentum of that particular molecule. Means in this motion, all the particles move with a different momentum. So with this momentum, each molecule collides, not only collides with each other, and not only with the neighboring particles along with the walls of the container. Okay. So with that momentum means each particle having mass and moving with a certain velocity. So finally that the particle or molecule moves with a certain momentum. So with this momentum, these particles will collide with the neighboring along with the walls of the container. So this force applied on the surface of the wall. Okay, we assume one cubical container. Okay, so each molecule moves with a certain force and hits the surface of the wall. Then that surface experiences some pressure, because the pressure is nothing but force applied per unit cross-section area. So the pressure exerted by the molecule on the container. So the cause for the pressure is the velocity of the molecule. So pressure exerted by the gas on the walls of the container. Right? So reason is what? Because the particle is moving with a certain velocity. So here comes, with this information, we can conclude that the molecule is possessed with a kinetic energy. Yes, whenever the molecule is moving with a certain velocity and with some mass, so definitely that molecule is possessed with certain energy is called kinetic energy. That is, we know the expression half mv square. And the theory explains the pressure exerted by the gas molecule due to the kinetic energy is called kinetic theory of gases. So here comes our introduction, means the title of the story, that this theory, the study of kinetic theories of the molecules, explains this nature, that is kinetic theory of gases. This is completely the kinetic nature of the molecule. Kinetic nature of the molecule. So this discussion is the title as kinetic theory of gases. So with this kinetic energy, the molecule's temperature also created in the container. Yes, for every collision the energy will be also released. Okay, so heat will be generated. right? So with this kinetic energy, it can create the temperature in the container. So this is just because of the velocity of the molecule. So all these are because of that may be a pressure, that may be a temperature, means heat generated in the container, is all just because of the velocity possessed by the particle. So it's nothing but kinetic energy is involved in that particles. So if this velocity of the molecule is more, then the kinetic energy is also more, so that the pressure and temperature also be more. So on the walls of the container, the pressure exerted by the molecules, with that the temperature also increases. So all these are just because of the kinetic energy possessed by the particles. So with this, if the kinetic energy means velocity is more, then the pressure exerted on the wall is also more, so that due to this collision, the temperature also increases. So all depends on the velocity of the molecule. Now, due to this motion of the molecules, we observe the various parameters like pressure, temperature, volume, energy, etc. Okay, so far just we discussed different situations. So in this situation that we obtain different parameters like pressure, perimeter picture, temperature, volume, energy, velocity. So all these terms that we discussed in this. So this kinetic theory interrelates because in the very beginning we discussed the microscopic properties and the macroscopic properties, this relation. So this kinetic theory gives the relation between the kinetic or the microscopic properties and the macroscopic properties. Here comes all the discussion that pressure, temperature, volume, energy, etc. So for every collision, the velocity of the particle changes. Yes, see for every collision, see initially if the particle is moving with a certain velocity, and the moment it is collided, then the velocity comes to means the particle comes to rest, the velocity vanishes, and after that again the direction will change and it moves in the different directions with the different velocities. So what we observe that for every collision, there will be a change in direction and also change in velocity. So the energy contained by the gas molecule is often displayed here. So the energies of the molecules with the different velocities is expressed like this. So for example, here in the gas, each molecule is moving with the half square kinetic energy, and so there are so many number of molecules or particles are present with the different velocities. That is nothing but what? Half square energies. So for example, one particle is moving with a v1 velocity, another particle is moving with a v2 velocity, like that v3, v4 and vn particles are present, because initially we assumed that there are n number of particles. So all are moving with different velocities, then they will be possessed with different kinetic energies. So therefore the average energy by the molecule is, okay, so average energy by the molecules is given. So 1 by n means we are adding up and dividing with n number. So that's what is here, 1 by n. Okay, all halves are common, m is also common, and all the velocities are variable, so they kept in the bracket that v1, v2. Okay, so this is the expression. And now let the average velocity be c. We are assuming that the average velocity be c here. So the energy is of this m v square instead of v. We are assuming that is the average velocity. So we combine all v1, v2, v3. Okay, so together we assume that is in c here. So let the average velocity be c and the energy possessed by the total, that half m c square now. So from the above equations we can get c half m c square is equal to, so here half m, we are adding up all these n number of particles, we are getting this. So it will be cancelled over here, so then c is remaining here. So m will be cancelled, m half will also be cancelled. And c is coming here and the root comes under this right hand part, comes under what? Under the root. So v1 square plus v2 square plus and so on to vn square by total number of entities, that n. So here this is called the root mean square velocity, that is RMS velocity. So what we calculated here, the velocity of the total number of particles in this, that is c, is the average. Okay, average velocity. And if you observe the mean, RMS, that is the root mean square velocity. So here observe this root, okay, mean means adding all these by squaring. Okay, root mean square, all squares. Root mean square velocity. This is RMS velocity. Okay, so here, due to this kinetic energy, see that kinetic energy is because of the velocity, right? So simply with this velocity, I told you that this cubical box experiences some pressure, so that also you can calculate how much pressure is exerted on the wall of the container, right? So the next type is pressure exerted by the gas. Okay, considering a cubical container of side A, okay, you can see the side here is given L, side A is given. Okay, has a n number of molecules, each of mass m. So let the capital M be the product of individual masses, that is n. N number of particles are there, and each mass is small m. So the product is total mass of that container. Now, at any instant of time, it has a momentum. So momentum comes into the picture because the mass is moving with the velocity. Momentum will comes into the picture, and this momentum moves in any direction, that is x-axis, y-axis, z-axis. It's a cubical one. So mc x, mc y, and mc z. Okay, so mass into velocity along x-axis, y-axis, z-axis respectively given. So total at any instant of time, the total momentum is mc here. Okay, so if we are considering any one molecule, for example, one molecule is moving in a particular direction, then in that direction, what will be the pressure exerted, that we are going to calculate now. So if it hits the plane, YZ plane, see here, this is x-axis, y-axis, z-axis, then YZ plane means it will be this one. Okay, so CFGB, right? YZ. So here, YZ plane with the velocity Cx, it's moving along x-axis. It's moving, so it's moving along x-axis. So Cx, then due to elastic collision, it rebounds with the velocity. Yes, particle is moving with a certain velocity Cx. Particle moving with a certain velocity Cx, and collides with this plane, for example. Then just we assume that YZ plane. And the moment it is collided and it comes back with the same velocity is called minus Cx is given here. So the change in momentum for one strike, see one particle is moving and collided with one side plane and comes back with the same velocity, and the net, that is the change in momentum for one strike is given here, that is mcx minus of minus mcx, that is total momentum for one strike is 2 mcx is one strike. Now the force on the YZ plane is due to one molecule is equal to, means we are calculating force exerted on that. See, this is actually Newton's second law, that is change in momentum is equal to force, that is rate of change in momentum. It's nothing but force that we know already learned in the Newton's second law concept, that the time taken by the molecule is 2a by c. Time is equal to displacement by some velocity here. So displacement in one direction is A, and it's also coming back as a 2A. Okay, so we consider one molecule is moving in cube from one side, it is A, and hitting, and after that it is coming back with a distance 2A, and is moving with the velocity Cx. If it is in C is the velocity along the x-axis. So it's a time. So 2A by Cx is the time, and the force due to the one molecule is dp by dt is given over here. So dp is the change in momentum, that is 2 mcx just now in the calculated, and dt is given here. So 2a by cx, and finally we are getting mc squared by a is what is the force exerted on the wall due to the one molecule. And the force due to n number of molecules here multiplying with the n here, so the same expression, and the pressure exerted on the zy, on the yz plane also. Okay, so the pressure exerted on the other planes also you can calculate. So here mc square, so here m and cx. So if it is in a y direction, so directions also changes like this. So similar, the pressure along y direction is mnc y square a cube. Okay, so see here pressure formula force by area, and here we got the force m, and area is a square. So multiplying with the a and a square, we are getting a cube here. So this is what similarly we are calculating for the y direction. So py is equal to mnc y square by a cube. And the other direction, the direction is also calculated, that is mnc z square by a cube. So total pressure acting on the cube in all the directions is, so adding all the pressures, that is along x-axis, y-axis, and z-axis, we are getting like this. Okay, so we're doing average like. So mn, all the commons are mn 3 a cubes and 3 is in the formula here, 3 a cube, and common means these are taken common, and the remaining added up, that is cx square, cy square, and cz square are added over here. and P is equal to 1 by 3 is taken common. So M and in the very initially we told you that we discussed that it is what total mass enclosed in the container, that is M, and A cube, okay, and velocity C square means taking all these as a common over here, right? So this is C square means the total velocity in the container is moving in all the directions is C square. Okay, and M by V, so V is the volume, A cube is the volume here. Okay, volume of the cube is A cube. So simply we are writing this as a M by V is the density of that container. So totally pressure exerted by the gas on the container on the walls of the container is 1 by 3 rho C square. This is an expression for the pressure. Okay, so now we will move on to the next one is the degree of freedom. Degree of freedom gives the information about in what direction the particles can move. Okay, in how many dimensions the particle can move is explained in this concept, that is degree of freedom. So degree of freedom, I told you, it gives the complete picture of in how many ways that particles can move. That may be a single particle, that may be a diatomic or triatomic, so different molecules. See, because the molecule is the composition of the number of particles. Okay, so for example, one atom is there or one particle is there, it can rotate in any direction, that x-axis, y-axis. So here is given some diagram that it can move either positive x-axis or negative, positive y-axis or negative y-axis or vice versa. So in moving in any directions. So this is what is the degrees of freedom. So here the definition can be given. The term degree of freedom of a system or a molecule refers to the possible independent motions a system or a particle can have, or the total number of independent ways in which the system can process the energy is called degree of freedom. Yes, so in how many ways the particle can move freely in the space, right? So this is called degree of freedom. So that depends on the type of the molecule. Maybe that may be a single atom, that is called monatomic, diatomic or triatomic. So based on that, the restrictions comes into play. So the independent motions are translational, rotational, and vibrational. Okay, so the particle can move in either of these three motions, that is translational, rotational, and vibrational. Right, so here are some examples that the monoatomic particle can have three translatory motions. So because this monoatomic is no way concerned to any other particle, so the motion is no way restricted. It can move in any directions. That monoatomic particle can have three all the translatory motions in space. Okay, here we can see the diagram that it can move in any direction. Now for the diatomic gas, it can have only two motions and the restriction, hence it has 5 degrees of freedom. Okay, here is given some expression here. So capital D here is the degree of freedom, and 3n minus r. R is what? Restrictions. How many restrictions are there? And n is the number of particles in that bond is given. So as per this expression, we can calculate the degrees of freedom. So using this, we can estimate the number of degrees of freedom. So for diatomic, is the 5 is the number of degree of freedom. Similarly, for the triatomic molecule, the total degrees of freedom is 6. Okay, triatomic total degrees of freedom is 6. Okay, triatomic means what? Here 3 restrictions will be there, and here number of particles will be present in triatomic is 3. So 3 into 3, which is a 9 minus 3 restrictions, so you get the 6 degrees of freedom. So this is a way how to describe the degrees of freedom of these particles. Okay, so in this formula, it is the degree of freedom. D is degree of freedom, n is the number of atoms, and n is the number of restrictions. And coming to the very important conclusion that kinetic interpretation of temperature. See, in this kinetic motion, the temperature is playing very important role. So for that, we are going to obtain the expression in terms of temperature now. So kinetic interpretation of the temperature just here. Also, just now we derived the expression for the pressure, that is 1 by 3 mnc square by v, right? V is equal to half mnc square by v. And where the gas B of 1 mole of substance consisting of n number of molecules. Okay, we are assuming now, we are calculating now, right? So in this case, we consider n number of molecules, then this expression will become what? The PV. See, I'm taking this V in this side, so PV is equal to 1 by 3 m n c square, because we considered 1 mole of substance that is consists of n number of particles. Okay, so the expression will be, see, already we know that PV is nothing but RT, and this n is taken this side, so RT by n, and the remaining thing is 1 by 3 m c square. Okay, so PV and RT that we know. So PV is equal to RT that we know. Okay, so and this N is taken this side, so RT by N is equal to 1 by 2 mc square. And now the expression for the kinetic energy that I already knew that K is equal to half mc square. Okay, and just this thing is we are multiplying with this one 1 by 2. Okay, see 1 by 2 and 2 by 2. See like this 2 by 2 and 1 by 2. Okay. Right, so in half mv square is multiplied with like this, and 3 by 2 mp here is an expression here. Okay, so 3 by 2 r by 3 by 2 r by n into t is equal to kinetic energy to multiply half mv square. So 3 by 2 r by n is nothing but another constant. See, r is constant, n is constant, and the taking this as another constant as a Boltzmann's constant. So 3 by 2 into constant into t is equal to k. So where k is a Boltzmann's constant and 3 by 2 kBT is equal to half mc square is nothing but what is again kinetic energy. And the relation between, see, if all these are constants, and relation between here temperature and velocity. See, our title is kinetic interpretation of temperature. So that is what temperature is directly proportional to the square of the velocity. That is T is proportional to c square. Hence, this is the relation between the temperature and the kinetic energy. Now coming to the specific heat of the gas. Specific heat of the gas is a very important parameter in this. Now at a constant volume, means we are calculating these things, keeping the parameters, some parameters as constant. Now at constant volume, the energy required to raise the temperature by 1 degree. The expression for the statement definition for specific heat of a gas is what at a constant volume, means keeping the volume constant, the energy required to raise the temperature by 1 degree. Okay, to raise the temperature 1 degree, so how much energy is required is given at constant volume. Delta V is equal to 0. Means keeping constant means what? Delta V is equal to 0. Hence, the energy, delta Q is energy, is nothing but energy. That is delta U. So delta Q is equal to delta U plus P delta V. So delta V is keeping constant. So this term will become 0. Then delta Q is equal to delta U is remained. And the total energy delta Q is given is used to raise the internal energy and the temperature. So degree of freedom for this is 3. See here we are calculating the specific heat of a gas for a particular system. Okay, now the specific heat CV. CV means what? Keeping the V constant is equal to dU by dt. That already will end 3 by 2 R. This is for 1 degree temperature. To raise for 1 degree temperature. Now the formula Cp is equal to Cv plus R. You know the formula relation. Okay, so Cv just now we got 3 by 2 R and plus R. So total it's a 5 by 2 R. So now this ratio, this is what gamma is equal to Cp by Cv. Okay, so that is equal to Cp is how much? 5 by 2 R and Cv is how much? 3 by 2 R. So we are getting 5 by 3 and the ratio is 1.67. So this is the value for gamma for monoatomic gas. So monoatomic gas. Okay, now coming to the for diatomic gas, degree of freedom is 5. Just we learned over there. Okay, so kinetic or internal energy per mole is 5 by 2 RT, and internal energy per molecule is 5 by 2 kT. So same applying for the remaining things, the same discussion that Cv is equal to 5 by 2 R for diatomic, and Cp is 7 by 2 R for diatomic, and gamma is taking ratio for this is 7 by 5. We are getting 1 by 4 is the specific heat of this material. And for the triatomic or polyatomic, so degree of freedom is 6 here. Okay, so degree of freedom is 6 already in the other diagram we have seen. And the kinetic energy per molecule is 6 by 2 RT, and per mole is 6 by 2, and per molecule is 3 by 2. And substituting the values means Cv is equal to 3R and Cp is equal to 4R, and you are getting gamma as 4 by 2 is equal to 1.33. So like this, if you know the degrees of freedom, you can calculate the specific heat of the gas. Now moving to the mean free path. Moving to the mean free path, the average distance traveled. The average distance traveled by the gas molecule between any two successive collisions is known as the mean free path. That in the very beginning we discussed it. Okay, mean free path means the average distance traveled by the particle between any two successive collisions. Right here, pictorially is given over here. That is, this is any molecule or an atom, that's an atom A, is moving in a particular direction with the velocity is given over here. And nearby B, atom B, two atoms are here. Okay, and the distance is nothing but the size of this atom A. Then definitely it makes collision. Definitely it makes collision. If the distance between them is exactly the diameter of this atom. So this is the collision cross section. Okay, understood the concept if I'm correct that two particles are there which are at a distance, diameter of this particle. If this distance between these two particles is more than the diameter of this, then there will be no collision. It will be straight away. It will move along. So mean path can be expressed as what? The total distance traveled. Total distance traveled between the successive collisions divided by total number of collisions. So here is the expression that lambda is nothing but mean free path. Lambda is expressed with what? Mean free path. So is equal to 1 by under root pi n d square. Under root pi n d square. Right, where pi root 2 are constants and n is number of molecules per unit volume. In a given unit volume, how many number of particles are present, and d is the diameter of the molecule. So if that d is more, then there will be no collision. So it can move freely, and so the mean free path can be explained with this formula, that is 1 by root 2 pi n d square. So total distance traveled between the successive collisions by total number of collisions. So with this, the chapter is concluding, and from this we are expecting mostly 2 marks question or 4 marks question are available from this chapter, right? So mostly the very short answers come into play. There is no deletion from this chapter. Okay, so in this academic year there is no deletion. So these are the major topics to be discussed. You need to follow through. So with this, this session is completed. So my dear students, very all the best for the examinations. Thank you.